Armstrong Flight Research Center did amazing things this year, helping advance NASA's mission to explore the unknown in air and space, innovate for the benefit of humanity, and inspire the world through discovery. NASA's X-57 Maxwell all-electric aircraft reached another milestone toward first flight. Lithium-ion battery packs were successfully installed and powered the plane's motors. Armstrong is advancing all-electric propulsion technology that will make aviation more efficient, quiet, and environmentally friendly. NASA and Lockheed Martin teams made great progress assembling NASA's X-59 quiet supersonic experimental aircraft. The crew successfully added the tail, completed final installation of the nose, performed a system check of the ejection seat, and installed the engine. Preparations continued for future X-59 flight tests that could open the door to commercial supersonic flights over land. Testing validated supersonic shockwave imaging and measuring systems installed in chase aircraft that gather critical data on the X-59's sonic thump. The chase aircraft also received a new life support system to provide pilots with enough oxygen during high-altitude flights. And testing was conducted to verify microphone stations that will be used to measure the thumps on the ground. Advanced air mobility is NASA's vision to map out a safe, accessible, and affordable new air transportation system. With the addition of new technology such as electric aircraft concepts and increased automation, NASA's mission is researching how industry aircraft can be integrated into the skies. Armstrong team members are leading testing, simulation, and information sharing efforts alongside researchers from NASA's other aeronautics centers. Armstrong is leading an effort to build a small-scale version of NASA's new hybrid electric aircraft concept for transport category aircraft. Flights were conducted to test the integrated flight, power, and propulsion controls approach. Armstrong's Flight Loads Laboratory completed one of its biggest loads calibration efforts with an FA-18E Super Hornet from Naval Air Systems Command. Testing helped establish design limits and ensure safety of flight and crew. 87 load cases were applied to exercise structural response. NASA is taking flight training and preparation to new heights at Armstrong's Simulation Laboratory. One-of-a-kind experimental simulations are providing researchers, engineers, and pilots with a safe environment to practice test conditions. The first phase of NASA's new flight data archiving and acquisition system was released to help engineers record, access, process, and analyze the vast amount of data collected during flight testing. This phase enables better support of X-59 envelope expansion flight testing. NASA Armstrong's C-20A aircraft conducted geological observations of California to document the long-term behavior of active landslides and the San Andreas Fault. The science aircraft deployed to Maine to validate soil moisture algorithms and to Alaska and Canada to study the effects of climate change on Arctic and boreal ecosystems. A group of university students and mentors flew aboard Armstrong's DC-8 aircraft to study air quality as part of NASA's Student Airborne Research Program. The DC-8 studied dangerous engine icing conditions at high altitudes and deployed to Cabo Verde off the coast of Africa to measure winds, aerosols, precipitation, and other conditions that influence convection. Armstrong's ER-2 aircraft supported NASA's multi-year airborne science campaign to track U.S. snowstorms. The high-altitude aircraft also studied how convective storm systems affect air pollution, ecosystems, and provided critical information on natural disasters such as volcanoes, wildfires, and drought. They also studied the amount of light reflected off the moon. The King Air B-200 science aircraft supported NASA's campaign to study small ocean whirlpools, eddies, and currents, and the role these ocean processes play in the movement of heat, nutrients, oxygen, and carbon from the ocean surface to the layers below. After 732 nights observing, NASA's SOFIA project ended September 29, 2022. SOFIA was a mission of discovery, revealing unseen and sometimes unseeable parts of our universe, including water on the sunlit surface of the moon, the first type of molecule ever to form in the universe, and the intricate magnetic field structures involved in the formation of stars and spiral galaxies. The Boeing 747 SP jetliner was modified to carry the 38,000-pound 100-inch telescope. Engineers at NASA's Ames Research Center developed a garage door-like mechanism that rolled up to let the telescope observe the skies. By 2014, the observatory reached its full operational capability. And for 8 years, SOFIA enabled astronomers around the world to study the infrared universe and unveil impressive cosmic events and objects invisible to other telescopes. NASA's Flight Opportunities Program supported suborbital flight campaigns, including parabolic flight testing innovations designed for a broad range of space-based capabilities, including 3D printing, medical care, biotechnology, food and farming, power systems, and propellant gauging. As part of NASA's TechRise Student Challenge, 57 student teams in grades 6 to 12 and their teachers designed and built space technology payloads to test on future suborbital rocket or high-altitude balloon flights. Winners of NASA's first Tech Leap Prize launched their technologies this summer on high-altitude balloon flights, testing Earth observation technologies at stratospheric heights. Thanks to Center Innovation Fund awards, NASA continues to create innovative solutions to address some of the most pressing aerospace challenges. New weather sensors were designed to measure atmospheric pressure, temperature, relative humidity, air quality, and 3D wind velocities. And a new magnetic connector that releases payloads quickly and reliably was tested and could have applications for aircraft, spacecraft, and space exploration. An early career initiative project team is researching how magnets can be used to attach and release cryogenic fuel lines and withstand the dust in the unforgiving environments of the Moon and Mars. Another early career initiative project team is testing highly elastic strain sensors to aid in the design of supersonic parachutes used for Mars exploration. This year, fiber optic sensing system researchers continued Armstrong's support of heat shield development. FOSS developers adapted their technology to support NASA's demonstration of an inflatable heat shield technology that could help land heavy payload cheaply on Mars. In 2013 and 2014, NASA Armstrong's Flight Loads Laboratory conducted structural tests on the donut-shaped inflatable device designed to more effectively slow down a spacecraft upon atmospheric re-entry to Earth or other planets. November's return from orbit demonstration was the next step in the technology's development. All eyes were on Artemis 1 in November.
And liftoff of Artemis 1.
The first launch of NASA's Mega Moon rocket, the Space Launch System, and the Orion spacecraft, as NASA builds a long-term presence on the Moon. Previously, NASA Armstrong played key roles in the Orion Launch Abort System developmental test, Orion parachute tests, autonomous flight control system testing, and the spacecraft Launch Abort System demonstration. This year, Armstrong's Global Hawk unmanned aircraft collected rocket systems health data during the Artemis 1 launch. And in preparation for Artemis 2, engineers are supporting development and integration of a system to collect heat shield data during launch. NASA Armstrong innovators, pilots, and mission support teams attended events geared towards inspiring the next generation of innovators. The center participated with exhibits and hands-on demonstrations showcasing aviation-inspired technology and the latest in NASA aeronautics research, space exploration, science, and more. That's Armstrong Flight Research Center's 2022 highlights. For more on these and other stories, follow us on the web at nasa.gov/Armstrong.